Today we're going to take a look at the reverse chain rule. The reverse chain rule does what it says on the tin. It's the chain rule, but in reverse. So that means rather than using it to differentiate, we're going to use it to integrate. So for example, if we wanted to integrate something like this, then if we can work out something which differentiates to get this, then we know the integral of the differentiated bit is going to be the original function. So our job is to find this thing, find this function, such that when we differentiate it, we're going to get exactly what's inside the integral. Then we get our answer, of course with a plus c. There are three methods that I can think of for using the reverse chain rule, but if you don't get on with any of them, then you can absolutely just use a substitution. Substitution will work for all reverse chain rule questions, but not vice versa. So if you're going to learn one technique, make it be the substitution. So one of the methods that we can choose is thinking about what might differentiate to give this bracket. So have a think through the functions that you know. What's going to differentiate to give you a bracket to the power of 6? Well, it's going to be a bracket to the power of 7, isn't it? And what do you think is going to be in the centre? Well, if you know and are confident with the chain rule, which hopefully you are, given that you're watching a video about the reverse chain rule, the same thing will be in the bracket as in the bracket in the integral. Let's try it out. Let's differentiate this and see what we get. So dy dx, remember, bring down 7 times by the derivative of the inside of the bracket, and then times by the bracket to the power of 7 minus 1, or 6 in this case. So we get 21, 2 plus 3x to the power of 6. So it's looking quite similar, but this 21 is not really helping us very much. So what we can do, we can apply a little trick. If we both times and divide the integral by 21, then now we're in a really good position, because this is equal to 1 over 21 lots of, well, this integral is exactly the same as what we differentiated, because as I say, the integral is the inverse of the derivative. So I'll say it again, if we know that 2 plus 3x to the 7 differentiates to get 21, 2 plus 3x to the 6, then backwards, the integral of 21, 2 plus 3x to the 6 is 2 plus 3x to the power of 7. Bit of a mouthful. This timesing and dividing malarkey will come up very often, so try and remember how to do it. You're always adding in a number that you want or need that you can compare to the derivative, and then dividing by the same number on the outside, because then you don't change anything. Let's take a look at example 2. Example 2's now got a sine x squared times by 3x all inside an integral. And again, we have to think through what might differentiate to give this. Well, how would we ever get a sine from differentiation? To get sine by differentiating, we know we must differentiate a minus cos. Maybe we don't know what goes in the middle, but that's at least our starting point, because the derivative of minus cos of x is sine of x. Now, if you know your chain rule, you'll know that the insides have to stay the same. So we'll leave this as x squared. I know there's a 3x out here, but if you know your chain rule, you'll know that something goes on with the derivative of this, and it looks suspiciously like 3x. So let's try differentiating it and see if we get close then. Take the derivative of the x squared to get 2x, and then the derivative of minus cos is sine, as we said before, with the x squared staying the same. It looks really similar again, but now there's a 3 instead of a 2. So what we can do is we can first bring the 3 outside, so then we don't have to deal with it, and then do the trick we saw before. Add in the 2, because it's exactly what we need to make it match up to the derivative, but then don't forget to divide by 2 so we don't change anything. Once we've done this, the answer will be 3 over 2 lots of, what's the integral of 2x sine x squared? Well, it's going to be this, minus cos x squared, with our plus c. We can simplify this one a tiny bit, minus 3 over 2 cos x squared plus c. So that's one of the methods. You might think it's a bit guessy because you have to know what differentiates. The more practice you do on it, in differentiation and integration, the more you'll recognise what you have to guess. But it's not the only method. There is another method. The formula for the chain rule looks a little bit like this. The derivative of f of g of x with enough brackets is equal to f dash g of x multiplied by g dash of x. So this second method is a formula method. If the formula works for you, then that's great. The formula is, well, take the derivative exactly as it's written on the right hand side, put a dx at the end, and the answer should be the inside of what we differentiated in the formula above. Like this, with a plus c because we're integrating. So it might look a bit menacing, but if a formula method works for you, then use that method by all means. Let's see an example with it. In this example, we've got the formula up above. That's not given in the formula book, so if you're going to use it, make sure you memorize it. And the example we're given is the integral of x e to the x squared dx. Now, if we look through the formula, we have to try and locate what is g going to be and what is g dash going to be. Well, do you notice that in the formula, g of x is inside a function? And that's exactly what we've got here. We've got x squared, which is inside e to the x. G dash of x is then on the outside. Does it match up? Is x on the outside the derivative of x squared? Well, no. So we have to use our usual trick. We have to add in the 2 and divide by the 2. So we ask that same question again. Now the g of x is x squared and the g dash of x is 2x. That's great, that's perfect. And the f dash of x is e to the x. So I'll quickly write that down. So the f dash of x is e to the x. The g of x is equal to x squared. We don't need to write down g dash of x, but you could do if you wanted to. Just to make sure it matches up, it might help. We do need f of x though. What is f of x? The derivative is e to the x. The integral is also e to the x. And let's put it all together. F of x is e to the x. It's of g of x, f of g, so we have to sub in g, so e to the x squared. And then what does the formula say? Plus c. And that should be it. Depending on how comfortable you are with the chain rule, you could also differentiate this. Just make sure you get to the same answer without the 2's and the halves at the end. I've got one more method for you, and this is my favourite method. This is the one I use. I think it's the one that could answer the questions the quickest, but might get a bit of getting used to. So try it, see if it works for you. If not, use one of the other methods, or simply use a substitution because it's always going to work. In fact, this method relies on the process of a substitution. So the formula from before said that the integral of f dash of g of x, g dash of x dx was equal to f of g of x plus c. What we did last time is we found what g of x was, made sure it matched up to g dash of x, found what f dash was, and then integrated it, and then put it all together, and then wrote plus c at the end just to finish off. This method will be very similar, but it will be the wordy version instead, like we saw when we saw how to use the chain rule in differentiation. So the wordy version will be, whatever integral you've got, let's say it's 2x times by 3x squared plus 1 to the power of 5 dx. The first step is make sure the derivative of the bracket is on the outside. In this case, we're looking at 3x squared plus 1 inside the bracket. Is the derivative of 3x squared plus 1 2x? Nope, not really. So what do we have to times by or add on in order to make that true? Well, the derivative of 3x squared plus 1 is 6x. So we need an extra factor of 3 here, which means we need to divide by 3 here. So the answer will be 1/3. And to finish off this method, you can use your substitution to check, but you can assure yourself that if the derivative is here, it will disappear according to the substitution, and all you have to do is treat whatever's left over as a normal function. For example, this is a bracket to the power of 5. How do we normally integrate that? We add 1 to the power to get 6, and we divide by the power of 6. But of course, it's not actually just a bracket to the power of 5. It's got stuff in it, so we have to copy and paste 3x squared plus 1 with a plus c at the end. And as usual, you can simplify this a bit. You can do 1/18 instead. So the idea is treat it like x to the power of 5. You add 1 to the power, you divide by the power, but you replace it with whatever was in there originally. As I say, it's a wordy version of the formula that was the second method. It might work for you, it might not. I'm going to give one last example with this method, and then I'll give you a few exercises for you to try with whatever method you like or with this substitution instead. So in this one, I'm looking at what's technically in a bracket because it's to the power of a half, and I'm seeing that the derivative of minus sine is minus cos. The outside of the bracket doesn't say minus cos then, so what are we going to have to do? We're going to have to add in a minus 1 to get the minus cos, but add in another minus 1 so we haven't changed anything. We don't want to change the question, we want to leave it all the same. So we've added 2 minuses, and now what that gives us is the derivative minus cos is straight away there, and there's an extra minus on the outside for us to deal with later on. So this will be equal to minus, and let's see what we're going to get. Use this method, and you know that this is the derivative of what's in this bracket here, then you can just trust it that it's going to disappear according to the substitution. You're just doing it all in your head. This bracket is 1 minus sine x to the power of a half. So how do you normally integrate that? You add 1 to the power, and then you divide by the power. What do we stick in the bracket? Just the same thing, copy and paste. Add on your plus c, job done. And you can see there's very little working there. It's all going through the process in your head pretty much. 2 exercises for you then. Try all 3 methods. Try just substitution or pinpoint a specific method that you like. Try them out. Let me know in the comments how you get on. Well, there you have it. That's how to use the reverse chain rule. Some students find it the hardest of the integration techniques. Let me know how you find it below. See you in the next one.